section 6.3, definite integrals and antiderivatives. So we're going to talk about properties of definite integrals. We're going to learn how to find the average value of a function and how that ties to the mean value theorem for integrals. And we'll start connecting differential and integral calculus. So we start with properties of definite integrals. Now that we know the definite integral is the area under the curve, so when we see something that looks like this, the definite integral from 1 to 2 of f of x dx, then we read that as the area under the curve from x equals 1 to x equals 2 of f of x dx. Okay, so that means the area starting at 1 and moving to 2, the area between the curve and the x-axis. So there's a bunch of properties that we can talk about quickly. The order of integration. So here we did the integral from 1 to 2. So generally we see the integral from a to b of f of x dx. And what our first rule tells us is that if we switch the order of the limits of integration, then we just switch the direction. So the negative, if we had the integral from b to a of f of x dx, then we would be going from the right end to the left. And it would be equal to the negative of the integral from a to b of f of x dx. So we always want to keep the idea of our conventions. Going to the right is positive, and going to the left is negative. Above the x-axis is positive, and below the x-axis is negative. Okay, so there's our first rule. Our second rule is the integral from a to a. Well, if we look at my little sketch here, that would be the integral from 1 to 1 of f of x dx, and we would have no width, so there would be no area under the curve. So that is equal to 0. All right. Definite integrals have a constant multiple property, just like derivatives, and we can pull that out in front. So the integral from a to b of k times f of x dx is the same as k times the integral from a to b of f of x dx. And that constant could just be a negative that we can pull in front. Sum and difference rules. We can break, if we were taking the area under the curve from 1 to 2 of x squared plus 2x minus 7 dx, we could evaluate this area under the curve by doing each of these integrals separately. The integral of x squared dx from 1 to 2 plus the integral from 1 to 2 of 2x dx minus the integral from 1 to 2 of 7 dx. That's the sum and difference property. Just like with derivatives, if it's addition and subtraction, we can do them all separately. Okay, the next rule is called additivity. Sorry, difficult to say. And what that means is I'm trying to find the area under the curve from 1 to 4 of f of x dx. I could find it, if I had enough information, I could find it by doing the area under the curve from 1 to 2 of f of x dx plus the area under the curve from 2 to 4 of f of x dx. Okay, so you would have to have the information about the area under the curve from 1 to 2 and 2 to 4. All right, and the next one, the max-min inequality. If the maximum of f and the minimum of f are the max and min values of f on the interval from a to b, then the minimum times f of b minus a is going to be less than or equal to the area under the curve, which will be less than or equal to the maximum of f times b minus a. Let me draw a picture to help us understand this one. Okay, so what this means, if there's some minimum value of f on the interval from a to b, so I'm going to say that's right here, and then there is some maximum value of f on a to b, which I'm going to say is right there, then the area under the actual curve will fall between the area under the minimum. So the area under the curve will be greater than or equal to the area under the minimum, and it will be less than or equal to the area under the maximum. So hopefully the picture was helpful. So the area under that red curve is guaranteed to be greater than our blue area, greater than or equal to our blue area, and less than or equal to our green area. All right, and then our last rule is called the domination rule. Let's take a look at that. F of x, let's see, if f of x is greater than or equal to g of x on the interval from a to b, then the area under the curve of f of x will be greater than or equal to the area under the curve of g of x. And an extension of that is if f of x is greater than or equal to 0 on a to b, then the area under the curve is greater than or equal to 0. So this is rather intuitive. If the function f is always above the function g, then the area under f will be greater than the area under g. That one seems intuitive. All right, so let's go take a look at using the rules of the definite integrals. So let's say we are given the area under the curve from negative 1 to 1 of f of x dx is 5. Area under the curve from 1 to 4 of f of x is negative 2. And the area under the curve from negative 1 to 1 of h of x dx is 7. And we want to figure out if we can each of these values down below. So find each of the following integrals if possible. So I would like to know the area under the curve from 4 to 1. Well, that is they have switched the position of the limits of integration here. And so if the area under the curve from 1 to 4 of f of x is negative 2, then the area under the curve from 4 to 1 is the negative of that, which would be 2. All right, area under the curve from negative 1 to 4. Well, we've got an area under the curve from negative 1 to 1, that is 5, and then from 1 to 4. So we could add these two together, 5 plus negative 2, giving us 3. Okay, let's see if we can do this next one. The area under the curve from negative 1 to 1 of 2 times f of x. Well, I have area under the curve from negative 1 to 1 of f of x, so this looks like 2, the constant can be pulled in front, times 5, plus the area under the curve from negative 1 to 1 of 3 times h of x. Well, I have the area under the curve from negative 1 to 1 of h of x, so this looks like 3 times 7. So 10 plus 21 is 31. We have enough information to find that one. Area under the curve from 0 to 1 of f of x. We have no information about the area under the curve starting at 0, and no way to tie it in between two of these. So this one we cannot find. Not possible. All right, from negative 2 to 2 of h of x. All we know is the area under the curve from negative 1 to 1. We cannot just double it because they changed the limits of integration. We do not have enough information to find out the area under the curve from negative 2 to 2. All right, area under the curve from negative 1 to 4 of f of x. That would be what we found up here, so that would be 3, plus the area under the curve from negative 1 to 4 of h of x, which we do not have. All we have is negative 1 to 1, so this one is also not possible. Okay, next thing we want to talk about is the average value of a function. So our picture looks a little funny, but let's think about what we have here. So I have my function, which is this red line f of x, and I am trying to find the average value of f on the interval from a to b. That means the average value of all the y values on this line in the interval from a to b? Well, we do know how to find the area under the curve of f of x from a to b, and I could highlight it right here. Okay, so the area under the curve of f I highlighted in green dots here. So that's the area under the curve from f from a to b. And the average value, it would make sense that the average value of f from a to b would be somewhere near the middle of our function from a to b. So I've hypothetically put it in as this red dashed line here. That is f of c. Well, the average value of the function is going to be equal to, if you look, the area under the curve from a to b of f of c, this rectangle that we get here, ends up being equal to the area under the curve of our function from a to b, because I have this triangle, which I'll highlight in purple. This triangle right here happens to be the same shape and size as this triangle right here. So you can visually see that the area under the curve of this rectangle, which would be f of c times b minus a, ends up being the same as the area under the curve from a to b of f of x dx, because that triangle is the same size and shape as the triangle we have under here. F of c is our average value, so if we want to find the average value of a function, we just divide the b minus a to the other side, and we get this. So the average value of a function, which I'll write up here, f of c, which is our average value, equals 1 over b minus a times the integral from a to b of f of x dx. You will need to know this. Anytime you're asked to find the average value, this is what we are doing. So if this was from 3 to 7, we would do 1 over 3 minus 7 times the integral from 3 to 7 of f of x dx to find the average value of the function in that interval. All right, and here it is summarized. If f is integrable, which means it doesn't have any large discontinuities, on the interval, closed interval from a to b, then the average, the mean value of the function from a to b is the average of f is 1 over b minus a times the integral from a to b of f of x dx. And then they phrase it just slightly differently and call it the mean value theorem of definite integrals. If f is continuous on the interval from a to b, closed interval, then there is some point c in the interval from a to b such that the average value is 1 over b minus a times the integral from a to b of f of x dx. It's just saying that the average value will exist if the function is continuous on the interval from a to b, the closed interval from a to b. All right. So that is all we have for section 6.3. Homework will be in Math Excel, and I will talk to you guys in class tomorrow.